The kernel buffer ring is a circular queue structure used for managing I/O operations within the host system memory space. It maintains a fixed allocation of memory pages, typically between 4 and 64 kilobytes per ring instance. The ring contains both read and write cursor positions, which advance monotonically through the allocated buffer space. Cursor overflow wraps around to the beginning of the ring without generating exceptions. Initialization of a kernel buffer ring occurs during system boot or module load time. The allocator reserves contiguous physical memory pages and maps them into kernel address space. A control structure is created adjacent to the ring, containing metadata fields for size, flags, and cursor offsets. The initial write cursor is positioned at offset 0, and the read cursor is set to 0. No initialization events are generated. Write operations append data to the ring at the current write cursor position. The operation first checks available space between the write cursor and the read cursor. If insufficient space exists, the operation blocks until the reader advances the read cursor. Data is copied byte by byte into the ring buffer. The write cursor is then incremented by the number of bytes written, wrapping to 0 if it reaches the ring size. Read operations extract data from the ring buffer beginning at the current read cursor. The operation checks available data between the read cursor and write cursor. If no data is available, the operation blocks until the writer advances the write cursor. Data is copied from the ring into the caller's buffer. The read cursor is incremented by the number of bytes read, wrapping around the ring size boundary, when necessary. Buffer wraparound behavior occurs when either cursor approaches the ring boundary. The wraparound is transparent to the caller and requires no manual handling. If a write operation spans the ring boundary, data is split into 2 segments, one before the boundary and one after. Similarly, read operations may require 2 separate copy operations when data spans the boundary. The cursor is reset to 0 after reaching the ring size. Synchronization between reader and writer uses atomic compare and swap operations on cursor positions. No locks are required for normal operation. The reader and writer may operate concurrently on separate portions of the ring. Contention occurs only when the read cursor approaches the write cursor. In high contention scenarios, the reader will block on a condition variable until space becomes available. Writer blocking follows similar semantics. Memory ordering guarantees are provided by sequential consistency semantics. All write operations to the ring buffer must complete before the write cursor is updated. All read cursor updates must precede any read of data from the ring. Volatile memory barriers are inserted automatically by the kernel. Relaxed atomic operations are not exposed to user code. The ordering is maintained across all processor cores in the system. Ring size selection affects throughput and latency characteristics. Smaller rings reduce memory footprint but increase wraparound frequency. Larger rings provide more buffering but consume more kernel memory. The optimal size depends on expected workload patterns and data rates. Typical deployments use rings between 8 and 32 kilobytes. Ring size must be a power of 2 to enable efficient cursor wraparound using bitwise operations. Back pressure handling occurs when the ring is full and no reader is consuming data. The write operation enters a sleep state, releasing the processor. A condition variable is used to signal when space becomes available. Timeout values can be specified to limit the blocking duration. If timeout expires, the write operation returns an error code indicating buffer full. The timeout default is infinite, meaning operations will wait indefinitely. Data integrity is maintained through careful cursor management and memory ordering. No data is overwritten until the reader has advanced past it. The write cursor always advances after data is fully committed. Read operations cannot access data that has not been written. Boundary conditions between full and empty states are handled correctly. The ring maintains invariant that read cursor is always less than or equal to write cursor in logical order. Multiple rings can be instantiated within a single process or across processes. Each ring maintains independent cursor positions and data buffers. Interprocess rings require shared memory mapping through the kernel memory management subsystem. Each ring requires a unique identifier for access control and permissions. Ring identifiers are typically assigned sequentially starting from 0. The maximum number of rings per process is limited by available kernel memory. Destruction of a kernel buffer ring requires coordination between all readers and writers. All pending I/O operations must complete before deallocation begins. The ring is marked as closed, and subsequent operations return error codes. Any blocked readers or writers are awakened and their operations fail. The kernel unmaps the ring from address space and returns the memory to the free pool. Destruction may not be instantaneous if references still exist. Error conditions include buffer full, buffer empty, and invalid cursor positions. Buffer full occurs when the right cursor approaches the read cursor and no space exists. Buffer empty occurs when no data is available between the read and write cursors. Invalid cursor positions result from memory corruption or programming errors. These conditions are reported through return codes and error flags. The ring enters a recovery state where cursors may be reset by the kernel. Performance characteristics depend on ring size, workload pattern, and system contention. Read and write latency is proportional to data size and memory bandwidth. Throughput scales linearly with available bandwidth up to hardware limits. Wraparound operations add negligible overhead due to efficient bitwise arithmetic. Cursor synchronization has sub-microsecond latency in uncontended scenarios. Contended scenarios show latency increases proportional to blocking duration. Debugging tools include cursor position inspection commands and data dump utilities. Kernel tracing can capture ring operations at microsecond granularity. Memory inspection reveals the current state of all cursor positions and buffer data. Logging is configurable per ring instance through debug flags. The default logging level produces no output. Maximum logging includes timestamp, cursor offset, data length, and operation type for every operation. Future extensions to the kernel buffer ring architecture may include adaptive sizing, per-core ring variants, and hardware acceleration support. Hardware acceleration would offload ring management to specialized I/O processors. Per-core rings would eliminate contention in highly parallel workloads. Adaptive sizing would adjust ring size based on runtime behavior. These extensions remain in planning phase and are not implemented in current releases. The current API is stable and will not change.